We spent the last number of weeks studying kinematics, and if you remember, we defined kinematics on the very first day of class as the study of motion without regard to what causes that motion. We spent the entire first unit talking about speed and distance and time and acceleration, but we didn't focus for 1 second on what caused an object to accelerate, or what caused an object to be moving at 10 meters per second, or what caused an object to move 100 kilometers. This unit, we're going to focus on what causes the motion. What causes motion? What causes motion? If something's not moving, you're not moving right now. You're sitting at your desk right now. You're not moving. What causes you or your desk to start moving? You have to apply a force, right. So dynamics, the unit that we're studying today and going forward for the next few weeks, is the study of motion with regard to what causes the motion, which is the study of forces. You guys remember what a force is? Like, how do you define a force? I know in grade 6 you did this unit on flight. You would have talked about forces in grade 6. You would have also talked about forces later on in junior high science, maybe even before that. But you've learned it as early as grade 6, maybe even earlier, what a force is. Ben? Yeah, that's exactly what a force is. A force is a push or a pull. It's as simple as that. That's the definition that you learned back in grade 6. That's still the definition. Okay, 5 years from now, if you're taking a major or an honors degree in physics, a force will still be defined as a push or a pull. It's as simple as that. Now, forces are what cause motion, but that's not the only thing that a force can do. In fact, there's 2 things that a force can do. One of them, well, we can say that it causes motion or it accelerates an object. Which includes the fact that it causes motion, right? If an object is at rest, then you apply a force on it and it's going to accelerate, it's going to speed up. But it can also go the other way as well. If an object is moving, then a force can cause it to slow down. That's acceleration. Or it can cause it to speed up from movement, speed up even further, which is acceleration. So the bottom line is 2 things. The first thing that a force can do is cause an object to accelerate. Speed up, slow down. Do you know that changing direction is also an acceleration? Okay, even if you don't change speed, if a car is going around a turn at 100 kilometers per hour and it remains at 100 kilometers per hour, it's still accelerating, because acceleration is based on the change in velocity, not the change in speed. And as long as the direction is changing, the velocity is changing. So speed up, slow down, change direction. They all fit within accelerating an object. That's the first thing that a force can do. Cause an object to accelerate, to speed up, to slow down, to change direction. But the other thing that a force can do is to deform an object. What do I mean by that, deform an object? What does that mean? The word deform, yeah? Yeah, change the shape of an object, right? If I, let's say I've got one of those exercise balls. You guys know what I'm talking about, right? One of those big red exercise balls. And I sit on that exercise ball. I'm applying a force on that exercise ball. But I'm not causing it to accelerate. It's not speeding up or slowing down. But what do I do when I sit on it? I change the shape of it. I deform it. Now, is it ever possible to accomplish both of these things with a force at the same time? Accelerate an object and change the shape of it? Of course it is. Give me an example of it. Give me an example of when you apply a force and it accelerates the object, but also at the same time changes the shape of the object. Yep. Yeah, absolutely. It's a perfect example of it. A car crash. Car is driving down the highway at, let's say, 100 kilometers per hour. It hits something. And what happens? Well, it changes shape. Obviously, it gets dented and deformed when it comes to that car crash. But it also stops. It also decelerates. So, of course, it's possible to do both. Another one? Absolutely. when the tennis ball hits the wall, it decelerates, and then it accelerates and speeds up again, right? But during that process, it also changes shape. A tennis ball actually becomes very small if you throw it hard enough at the wall. A golf ball. Do you know that a golf ball, when you're sitting on a tee, if you hit the golf ball, let's say you're a good golfer, and you hit the golf ball, say 300 yards, let's say, 250, 300 yards. Do you know that if you took like slow motion video, like super slow-mo video of the golf ball, not only does it accelerate at an incredibly high rate as it hit with the club, it also deforms. The golf ball actually becomes about half its normal size as it's hit with the golf club. So it deforms dramatically, but it also accelerates dramatically as that force of the club acting on it is applied. That make sense? So it can do this, or it can do this, or it can do both. Let's define another term, the net force. The net force is the total force that acts on an object. And we include with that the direction. So in other words, we include with that signs, positives and negatives. Net in general means total. Today's 21st of March. I get paid tomorrow, actually. I get paid tomorrow. And when I get paid, I'm going to get a pay stub, which if you have a job, you know what I mean by a pay stub, right? The pay stub lists the number of hours worked and the rate of pay. It also lists, if you get any extra, like a bonus. It also lists money they take off for things like employment insurance. Sometimes they take off money. They take off a lot of money for adults, for income tax. They take off a bunch of mine for a pension plan. They take off a whole bunch of mine for a whole bunch of different things. Okay? My net salary is the total salary that I'm left with after everything is added together, including the money that's taken off, including the things that are taken off. Okay? So I say, let's say my base salary, let's say, is $500 a month. Okay? We call that my gross salary. $500. But then we add to that, well, we get a bonus because I'm just so good that I get a $100 bonus, okay? And then, well, they give me another couple $100 because, well, they feel sorry for me. So now I'm at $800, but now they take off like $200 for taxes. We're going to add negative $200 to it for taxes. They're going to take off $300 for employment insurance. And they're going to take off $280 for pension. Now, what's my net salary? What's my net salary? My total salary at the end of the month? 500 plus 100 plus 200 plus negative 200 plus negative 300 plus negative 280 gives me $20. So we call that my net salary because it's my total salary, which is ironic because this number up here that's actually called your gross salary, this is what should be called your gross salary. This is what should be gross when you see what you have left after they take off all this money for taxes and so on. But that's not what it's called. Your net is the total after you add everything together, including the positives and the negatives. The net force is the total force after you add all of the forces together, including the positives and negatives. So let's say Jacob pushes on Rachel's desk with a force of 20 newtons to the right. Okay? Christine pushes on her desk with a force of 10 newtons to the right. I push on Rachel's desk with a force of 5 newtons to the left. We had 20 newtons to the right, 10 newtons to the right, and we had 5 newtons to the left. We add those together, and we end up getting a net force of 25 newtons to the right on Rachel's desk. Does that make sense? The net force is the total after we account for all of the positives and all of the negatives involved. Net is always total. In the context of force, the total force. Another term, holy cow, it just keeps going here. Inertia, we defined this yesterday towards the end of class. We defined it as a tendency of an object to basically to keep doing what it's doing. A tendency of an object to resist a change in motion. Objects are kind of lazy. Like, if they're at rest, they just want to stay there. They don't want to do anything. They don't want to change their motion. Hey, I'm happy doing what I'm doing. If they're moving, then they just want to stay moving. They want to keep doing what they're doing. Objects that have mass have inertia. They have a tendency to resist a change in motion. Inertia is dependent upon the mass. The more mass an object has, the more inertia an object has. So, for instance, I have a certain amount of inertia right now because I have a mass of about 73 kilograms. If I was running down the hallway, then I would have the exact same amount of inertia, the exact same tendency to resist a change in motion. Why? Because I have the exact same mass. But on the other hand, if you look out in the parking lot and look at a car, it has a lot more inertia, a lot more tendency to resist a change in motion because it has more mass. And if it's moving down the highway, clearly it has more inertia, harder to stop, because it has a higher tendency to resist a change in motion, higher mass. What does the word equilibrium mean to you? Yeah?
It's when both sides of the equation are balanced.
Balance. Okay, balance. That's the word I'm looking for there. Balance, equilibrium. We talk in Physics 30, we have this list of things in Physics 30 that we have up on the board over here. This little thesaurus, this physics thesaurus. You can see the word equilibrium goes with balanced forces. Okay, static equilibrium means that we have balanced forces. Static means not moving. So when we're in a condition of static equilibrium, we say that we have all forces are balanced and the object is at rest. The object is at rest and the forces are balanced, so what's the object going to do? It's going to stay at rest. If you're in static equilibrium and the object is at rest, it will stay at rest, always. Now, if you all of a sudden have an unbalanced force, well then it won't stay at rest, but now you're not in a state of static equilibrium. Static equilibrium only occurs when the forces balance each other. As soon as that condition is gone, you're not in static equilibrium, and now it can move, now it can accelerate. Translational equilibrium, on the other hand, equilibrium means, again, somebody? Equilibrium means what? Balanced forces. What do you think translation means? Translational or translation? Moving equilibrium? So we're saying that we've got an object that's moving, but the forces are balanced. If the forces are balanced on an object that's moving, it will keep moving at a constant velocity. That's a little bit counterintuitive for some people. If the forces are balanced, there's zero net force, isn't the object going to stop? No. An object in motion will stay in motion forever at a constant velocity as long as the forces are balanced. It's not a force that causes something to stop. It's an unbalanced force that causes something to stop. So if we're in a state of translational equilibrium and the forces are balanced, it's going to keep moving at a constant velocity forever and ever and ever. Well, unless there becomes a net force, unless the forces become unbalanced somehow. Let's put these things together in a law. We'll call it Newton's first law, or sometimes called the Law of Inertia. It has two parts to it, which are really just a summary of what we've already said. The first part, part A, says an object at rest will remain at rest forever, until, at least, it's acted upon not by a force, okay, not by a force, by an unbalanced force. It can be acted upon by 50 forces and stay at rest, as long as those 50 forces balance each other. Okay, Rachel's desk is at rest right now. If Jacob pushes on it with 10 newtons to the right, and I push on it with 10 newtons to the left, what's going to happen to her desk? It's going to stay at rest, right? Why? Because those two forces that Jacob applied and I applied balance each other. The net force would be zero. The forces would balance. The object at rest stays at rest because the force is balance. But if Jacob applies a force of 12 newtons and I apply a force of 10, well, now that the forces are unbalanced, now what's going to happen? Well, her desk is no longer going to remain at rest. It remains at rest forever until Jacob applies an unbalanced force, until Jacob's force beats mine, and then it accelerates. An object at rest remains at rest until acted upon by an unbalanced force. Similarly, an object in motion, by the way, this is static equilibrium. An object in motion will stay in motion at a constant velocity. And what do we mean by constant velocity? We mean same speed, straight line. It's not going to speed up. It's not going to slow down. It's not going to change direction. It's going to remain at a constant velocity until acted upon by an unbalanced force. Cars traveling down the highway at 100 kilometers per hour. Guess what? There's wind resistance, air resistance acting on that car. That's a force. But as long as the force of the wheels on the road pushing it forward are equal and opposite to the force of the wind, the force is balanced, and the car is going to keep going at 100 kilometers per hour. The only way the car is going to slow down is if the wind resistance, the air resistance, is greater than the force of the wheels on the road. The only way it's going to speed up is the other way around, if the force of wind resistance is less than the force of the tires on the road. As long as those two forces balance, it's going to keep going at a constant velocity, same speed, straight line. We call this translational equilibrium. So the first law, the law of inertia, is really two laws combined into one. We could say it's the law of static equilibrium, and we could say it's the law of translational equilibrium. Okay, I'd like everybody to have a look at these check and reflect questions right now. Page 142, questions number 1 to 4 and 6. We'll give you a few minutes to work on those right now in class, but not the rest of class, just maybe 5 to 10 minutes, and then we'll keep going on a little bit of Newton's second law after you finish these 5 questions. Okay, let's take a look at question number 3 here and number 4 as well. Number 3 says, use Newton's first law to describe the motion of a car that attempts to go around an icy curve too quickly. When I was 16, when I was your age, I guess, I got a job, best job ever for a 16-year-old. I got a job driving a delivery van. Worked for a dry cleaner and delivered dry cleaning all over the place. So every Saturday my dry cleaning run would be between 400 and 500 kilometers, which was perfect for me, for a 16-year-old who loved to drive. I got paid to go driving all day. Well, I remember the one time when I had turned 17 by this point, but still young, had been doing my job for a little while, coming off the highway where the speed limit was 100 kilometers per hour, driving on the highway at 100 kilometers per hour. There's a little bit of snow on the highway, a little bit of slushy snow, but it wasn't real slippery. It was fine in terms of maintaining control and so on. Here's the highway, but then I had to turn off into this little town. and I had to turn off on this exit off the highway into this little town. The exit comes down like this, and then it was going to join up with this road down here that went underneath the highway. That make sense? And then I was going to go down here and into this town and make some deliveries. So this is what I was doing, going 100 kilometers per hour on this highway, and then I come off onto this off-ramp, and I slow down, like you always do when you go onto an off-ramp, right? But at this point, it was about right here, I hit a patch of ice. And what happened? In a sense, I lost control. It didn't go crazy. Like, it wasn't like I hit other cars and flipped over and whatever. But it wasn't that bad because I wasn't going that fast. I had slowed down. But still, when I hit that patch of ice, the forces now were balanced. Why? Because there was no friction acting on the car or on the van, causing it to change direction, causing it to go in a turn. So I went in a straight line. Newton's first law says an object in motion will stay in motion at a constant velocity. That means constant speed, straight line. So if I was going at, say, 40 kilometers per hour on this off-ramp, or let's say 30 kilometers per hour on this off-ramp, then when I hit that patch of ice, I kept going in a straight line at 30 kilometers per hour. That's Newton's first law. That's a state of translational equilibrium. The forces were balanced. Okay, there was maybe a little bit of friction, but not much. Okay, nothing to change my direction, nothing to change my speed. Forces were balanced. I was in translational equilibrium. I kept going in a straight line. Until what? I hit the guardrail. That's exactly what happened. Until I hit this guardrail that goes around it, right? Which applied an unbalanced force, which caused me to not be in translational equilibrium anymore, which caused me to come to a stop. Okay? Make sense? Okay, let's take a look at that second one. Second part of that question now, which said Newton's first law to describe a lacrosse ball after leaving the lacrosse stick. Well, as it leaves the lacrosse stick, it was at rest, right, on the lacrosse stick. But as it leaves the lacrosse stick, it's clearly not at rest, right? It's accelerating. It's speeding up. Well, what do we know about the forces acting on it if it's speeding up, leaving the lacrosse stick? It must have an unbalanced force, right? The forces can't be balanced, otherwise it wouldn't speed up. Otherwise it would have remained at rest. So the forces are unbalanced, allowing it to speed up. But once it leaves the stick, what happens to it? No, doesn't slow down until it hits something. It goes effectively at a constant speed, which means that it's in, once again, translational equilibrium. It's going to keep going at a constant velocity until acted upon by an unbalanced force. Does that make sense? Let's look at number 4. It says, apply Newton's first law on the concept of inertia to each of these situations. The first one here is exactly the demonstration that we did in class a little while ago. How could you remove the newspaper without toppling the plastic beaker here? Do it really quickly, right? If you do it really quickly, then the net force acting on the beaker will be 0. And what's going to happen to it? It's going to stay at rest, right? It's in a state of static equilibrium. It'll stay at rest because there's no unbalanced forces acting on it. B says, while moving at a constant speed on a level snowy surface, a snowmobiler throws a ball vertically upward. If the snowmobiler continues moving at a constant velocity, the ball returns to the driver. Oh, this is a good question. I love this one. Why does the ball land ahead of the driver if the snowmobile stops? So here's the snowmobile. We'll just draw it as a little box here. Okay? It's moving at 5 meters per second, let's say. Here's a ball. I throw that ball up into the air. Actually, let's say that the snowmobile is at rest first. If I throw that ball up into the air, the ball comes straight back down. Agree? If I'm moving at 5 meters per second, this way, and I throw the ball what I perceive to be straight up into the air, I'm giving it a velocity of 5 meters per second up, but also, or whatever up, but also a velocity of 5 meters per second to the right, caused by the initial velocity of the snowmobile, right? So the ball ends up going like this. Now when it comes back down, where's the snowmobile? Right there. So from the perspective of the snowmobiler, what's happened to this ball? Okay, you're standing there watching this happen off to the side somewhere. You see this. You see the ball go in a parabola like this, right? But now let's say you're on the snowmobile. What do you perceive? The ball goes straight up and straight down. Because clearly the ball is going up. As the snowmobile went from here to here, the ball went from here to here. So it still looks like it's right above you. And then the snowmobile went to here, and the ball went to here. And the snowmobile went to here, and the ball went to here. So it makes it look as if the ball, from your perspective, is going straight up and straight down. Does that make sense? There's no unbalanced forces acting on it horizontally. So it's going to keep going horizontally at a constant speed of 5 meters per second. Okay, good? All right, I want to take a look at one more law here, and then we'll wrap it up. This one's called Newton's second law, but I'm going to ask you a couple questions before we explain what Newton's second law is. You guys know what acceleration is, right? How quickly velocity changes. What does acceleration depend on? In other words, what affects acceleration? What makes acceleration bigger or smaller? Give me one thing. Okay, the amount of force, the amount of unbalanced force. If I apply a tiny little force on Jacob's desk, I might cause it to move. I might cause it to accelerate a little bit. But if I apply a really big force on Jacob's desk, I cause it to accelerate at a much higher rate. Agree? What does acceleration depend upon? The net force. The bigger the net force, the bigger the rate of acceleration. What else? What else? Somebody said it. I heard him. Mass. The bigger the net force, the bigger the acceleration. The bigger the mass, the smaller the acceleration. Newton's second law says that the acceleration of an object is directly proportional to the net force. In other words, as net force goes up, acceleration goes up. But it's inversely proportional to the object's mass. In other words, as mass goes up, the acceleration goes down. So we're going to say that A, the acceleration, ends up being equal to the net force over, it's directly proportional to the net force, so A is equal to F net over the mass, because it's inversely proportional to the mass. Newton's second law says this in words, and mathematically, it just says A is equal to F over M. By the way, on your data sheet, the next equation you see on your data sheet is, under dynamics, F is equal to M times A, which you can see is just a rearranged form of the equation that we just wrote down there. Here's our example, the only one we're going to do here. Example 3.5 means it's in chapter 3 if you're downloading the textbook, on page 149. It says a lacrosse player, I don't know what it is with lacrosse, they seem to like lacrosse here, right? Exerts an average net horizontal force of 2.8 newtons forward on a 0.14 kilogram lacrosse ball while running with it in the net of his stick. Calculate the average horizontal acceleration of the ball while in contact with the lacrosse net. We're going to write down some givens here. We know that the force, the net force, is 2.8 newtons. We're going to say the mass of the ball is 0.14 kilograms. We're looking for the acceleration. Now, this is really a group B problem, right? It's accelerating. We still have our group B equations from last unit. A is equal to delta V over delta T. VF squared is equal to VI squared plus 2AD. They're all valid. But now we have another group B equation. We have an additional group B equation. And that is F is equal to M times A, as it appears on our data sheet. If we want to solve for A, we've got to get rid of M. How do we do that? It's multiplied by A, we divide it. So we say A is equal to F over M. And by the way, in this equation, F stands for the net force. Sometimes we don't write that little subscript beside it, but that's what it means. The net force is 2.8 newtons. Divide it by 0.14 kilograms. And that's going to give me 20 meters per second squared. Now, there's going to be times when you have problems that are tougher than this. When you have to use F is equal to m times a, but you also have to use d is equal to VIT plus 1 half AT squared in combination with it. Or a is equal to delta V over delta t, or VF squared is equal to VI squared plus 2AD. Just like you did in the last unit, though, look at the question, say, oh, this is a group B problem. I still have all those other equations that I learned last unit, but now I have one more that I can try. Sometimes one equation works, sometimes you got to use 2 or 3 different equations. Just do what you can. And if what you try first doesn't work, what should you do? Try again. Just don't use what? Group A. Don't use group A. Don't use V equals d over t, because as long as it's accelerating, you got to use group B. All right, take a look at these two questions on page 149, and when you're done for the day.